All right, all right. Time again for a little bit of learning for you guys. This is going to be on objective 1.6 in Unit 1. So this is on photoelectron spectroscopy. Just like our mass spec objective, this is basically all about being able to read a graph. Photoelectron spectroscopy is based on electron configurations, essentially. Okay, so, I guess I could present. All right, so when we make these graphs, they do so by basically subjecting atoms to high energy ultraviolet or X-rays. And when they do that, those electrons are going to absorb enough energy to overcome their attraction to the nucleus. Okay, so essentially they're being ionized. We are using our ionization energy here. This is called the photoelectric effect, which is why it's called photoelectron spectroscopy. So essentially, we're going to throw a ton of energy at an atom, and we're going to calculate or record how much energy it takes to remove each electron. Our outermost electrons are going to require less energy to be removed than our innermost electrons, who are closest and most attracted to that nucleus. And that's what this says here. Electrons that are going to be closer to the nucleus are harder to remove and will take more energy, while valence electrons are going to be the easiest to remove. Let's remember that vocab word, valence electrons, is for our highest energy level. We don't need that. All right, reading the graph. So reading the graph is not complicated, but it takes some getting used to. So your y-axis is going to be your number of electrons in that subshell. So this is really going to be graphing essentially electron configurations. So each peak you see will be for a subshell. And so whether that subshell has 2 electrons in it or 6 electrons in it will change the height of that peak. And then our x-axis is going to be our energy it took to remove that electron. So basically our ionization energy. The weird thing about these is that the bottom, our x-axis, is essentially backwards. So our most energy is going to be like where 0 would usually be. And things that are easy to remove are going to get plotted way over here on the right. The reason for this, and actually I don't know if it's the reason for this, what's nice about this is it means you can essentially read the peaks in order of an electron configuration. Because if you think about an atom, we always start writing our electron configuration at 1s. Well, those are going to be the innermost electrons. And the innermost electrons are going to take the most energy to release. So let's look at an example. This says the same thing. So height tells us the relative number. Lots of energy to remove the electrons on the left, a little amount of energy to remove the electrons on the right. So if we look at this, we have 1, 2, 3, 4 peaks. The most energy was required to remove these electrons here. So those are the ones that are closest to our nucleus, and we know that our first energy level only has one possible sublevel. So this would be our 1s sublevel. If this is our 1s sublevel, and it's full, clearly, because we have electrons that are further than that, this height must correspond to 2 electrons. So this is my 1s2. The next most would be our 2s, and it's the same height, so 2s2. 2p6, and we know this is 2p6 because we have electrons afterwards, so we know that we must have filled up that p. So far electron configuration would be 1s2, 2s2, 2p6, and then We have another. After 2p6 would become 3s, and we notice that it's the same height as the other two. So this is our 3s2. So the atom that is drawn here, or depicted here, must be magnesium. Let's look at more. So these are what real ones look like. Is the I'm not going to delete it. But the one on this top right is if you actually put it in a photoelectron spectroscopy machine. This is what it would print for you. It's not nearly as pretty as the ones that we put in books for you guys, because reality is never as easy to read. So here we have 1s2, 2s2, 2p6, 3s2, 3p1. So you notice how we can guess that that's 1 because it is half the height of our 2. So we can figure out what that is. In this PES, they're telling you something here. So they're saying this is the peak that is made by potassium's 3s electrons. This is the peak that would be made by sodium's 3s electrons. And they might ask you to explain that phenomenon. So what we could say is that potassium has more protons in its nucleus, so the higher positive center is going to, according to Coulomb's law, hold those electrons more tightly because of the increased charge and increased attraction, compared to the fewer protons that are in sodium's core. Okay, because we're looking at the same type of electrons, both of them are 3s. If potassium is held more tightly, which we can see because the binding energy is higher, it must be because of the greater core, the greater positive core. Okay. And this is also shown here. So if you look at these PES all put together, so we have hydrogens up here. So hydrogen only has a 1s. Notice how it is a little short peak because it's a 1s1. Its binding energy or ionization energy is that 1.31 megajoules per mole. Whereas as we add more protons to our nucleus, that initial binding energy gets higher and higher. That is because of Coulomb's law. There's greater attraction with a greater amount of charge. All right, given the spectrum below, which best explains why scandium commonly makes a 3+ ion as opposed to a 2+ ion? All right, so what this graph is showing, and remember, you want it to reference the spectrum shown, because it says, given this spectrum, what best explains why it would make a +3? So it should have something to do with ionization energy or the spectrum, okay? So A says removing 3 electrons releases more energy than removing 2 electrons. Well, this part on the bottom is indicating energy that had to be put in to remove the electrons. So it's not going to release energy at all. So that's A's out. B is a tempting answer, but you wouldn't need a photoelectron spectroscopy machine to help you with this. This one says scandium is in group 3 and atoms only lose the number of electrons that will result in a noble gas configuration. It's a helpful fact, but it's not, it doesn't, nothing about this helps with that. And then D says removing 2 electrons alleviates the spin pairing repulsions in the 4s sublevel. So it's not energetically favorable. And if it's alleviating repulsions, that seems like it would be favorable. Either way, spin issues have nothing to do with photoelectron spectroscopy. So C here says the amount of energy required to remove an electron from the 3D, which is our peak here, is close to that for the 4s. They're like right on top of each other. But there's a big gap to the next. So these are essentially the same amount of energy. So if you're going to have enough energy to remove some, it'll probably be all. That would be a very specific amount if you could only reach one of those peaks and not the next one. So it's because they have close ionization energies. And this is your practice with this. So using electron configuration, try to figure out what the electron configuration for this element would be.